All right. So, internet censorship and surveillance. My bigger area is thanks Amreesh for the introduction. My broader area, as you rightly put out, is anti-censorship, uh, building systems to evade censorship, anti-surveillance, network privacy, anonymity, and everything related under the within that umbrella. So generally, what is really internet censorship? I mean, I don't need to explain in great depth because I believe the audience understands what internet censorship is about. But the fundamental point of internet censorship, how it is distinguished from, let's say, firewalling, an organizational firewalling, is that internet censorship requires or actually entails state-sponsored firewalling. You can say, let's say you are the administrator of an organization, a private organization. You have your own firewalling rules. We don't really call it censorship because that's a private network. It's like my house, my rule, my territory, my rules. That's fine. That's within within your you're fully in control to restrict and allow whosoever you want and what kind of internet access you give to anybody. But we're talking about a state level censorship. No, we're talking about a bigger thing where a country level censorship happens. The country or the nation state decides to filter user traffic, surveil users, peek into their all sorts of data. They can surveil the data, stuff like that. By and large, most mechanisms so far, one obviously is the IP filtering. Others are DNS blocking, keyword filtering, DPI, deep packet inspection. Now, realize all these terms you're seeing here, DNS blocking, IP filtering, keyword filtering, DPI, this is all the same terms you also see in firewalling literature. Right? It's so really not different from firewalling and IDS systems, etc., which actually look at your network traffic and perhaps block some of it. But why is internet censorship particularly more relevant? Not only is because it's a state rule, it's a state-sponsored phenomenon, but also the fact that as per United Nations 32nd General Assembly, Article 19, and the Indian Constitution, Article 19A, both of these documents, they enshrine free speech on the internet as a fundamental human right. So it's no more just it's no more something a privileged person in a first world country may expect. It's now considered a fundamental human right to block free speech. And I saw in the list of talks today, there's somebody who will talk about internet shutdowns. Even internet shutdowns, like India has actually turned out to be the internet shutdown capital of the country. Now, when the internet shutdown, the longest shutdown which happened in India was in Kashmir between August 5, 2019, and I think February 5th, 2021. It's like 18 months shutdown they had. In initial 6 months, initial 6 months, there was absolutely no connectivity, nothing, not even 2G connectivity, etc. And that had a dramatic impact on the on various aspects of life. It can be from healthcare management to COVID pandemic information dissemination to doing online e-commerce, what have you. So there is enough material to be studied into internet censorship, primarily the mechanisms, etc., and not merely so internet censorship does not really come into the picture the moment we talk about internet dissidents. Generally, it will always be there. I mean, if it's somebody is going to do an internet shutdown, that will impact not only dissidents, but it's also going to impact regular users who may have actually been paying for the internet connectivity. So without much ado, I'll move ahead. These are the usual, we generally consider these as the usual suspects for internet censorship. But now we have a new kid in the block who has slowly evolved its censorship mechanism over the past few years. It started with simple website filtering, DNS filtering. Now it has gone to HTTPS filtering. So far, we have not seen the more advanced form. What is, I believe, in some place in China, you have ESNI filtering. I'll talk about that. We have not seen that yet happen in India, but I don't know how long we're going to be immune to that as well. There's of course the strange thing which most security researchers are not somehow they don't touch it with a 10-foot pole. That is about this tool which has come out, which goes and infects mobile. It's like a malware which infects mobile phones and captures all your data and exfiltrates that somewhere else. Nobody's really talking about that. Even, I mean, I'm very curious to know about it. The other thing which a lot of people in the thing is, majority of research on internet shutdown focuses on particularly one country. they don't realize that there's also a country which is also slowly evolving and upping its censorship capabilities. Like, for example, the point one here on the slide is talking about what we have in India. Point two is what we call the cache wall, Great Firewall of Kashmir, which not only does traffic filtering, it does VPN filtering. Of course, you have seen shutdown and internet blackouts. What are and also there are anecdotal evidences of internet throttling. Like, they can identify people who are having a voice call, internet voice call, and they'll slowly throttle it so that the quality degrades, and after that you can't use it. Selective SIM association dissociation. If the state suspects that you are whatever, if you are under the state's suspicion, they can allow the SIM to associate, not to associate. It's completely under the control. You see that there's a signal coming to your phone, but you just can't latch on to any network. So the outline of talk, I'll talk about the potential of, so how this is really talking about how we went ahead, what we have been doing the past few years about internet censorship, how we've been studying it. We study about, firstly, back in 2017, 16, 17, we were looking at the potential of large scale censorship. Then in 18, we saw actually how censorship first time, really works in the country at various, from the point of view of various ISPs. How to bypass them. One way, obvious way, is VPNs and Tor and stuff like that, but there are also more easier ways than that. Since 2020, we have also now started seeing internet. Sorry. Since 2020, we are also seeing censorship of HTTPS, TLS censorship. Along with that, an interesting phenomenon which happened last year was the government had banned 220 Chinese apps from the country. Now, one might feel that they may have just gone and pulled it off the app stores like Apple and Google Play Store. It turns out not only did they do that, they also apparently coerced these organizations to identify Indian users by looking at their SIM information and block them. I'll talk about this, in today's talk as well. So before I go ahead, for those who don't, I'm guessing most of you know, but still to make it brief, how the internet really looks like. The internet really looks like this strange, blob you're looking here. The red and the green ones are the ones which we call the tier 1 and the tier 2 ASs. These vast majority of these purple and blue ones are what we call the edge ASs, and the edge, the tier 3 ASs and the edge autonomous systems and users. So internet roughly is divided into these autonomous systems, which are basically they're really abstractions. There's nothing called an autonomous system per se in physically. There's nothing like that. So like an abstraction, a lot of like an organization, like an ISP, that would be called an AS, and it would have a ASN, an AS number associated with that. So what you can see by and large, the internet looks like it's like a hierarchical structure. Like, there are these central nodes which have very high degree of connectivity with others, and then at the edge you have these edge customers and edge ASs, like your local ISPs, which don't have too many peers it connects with. The problem we were looking at is that the big problem we were looking at in 2017 was that are there few positions in the country where the government may choose to install their censorship middle boxes and filter large fraction of traffic, because looks like the structure is hierarchical. In other words, should ordinary citizens worry that the government can go ahead and do large scale censorship or not? Answer to this question will come later towards the end of this talk. So before we move ahead, I want to briefly talk about a little bit about how how did we generally go about finding these ASs? What we did is, to answer this question, we first had to create we had to create an AS level map of the country. From the AS level map, and there are algorithms for doing that. From the AS level map, we identified the most frequently appearing autonomous systems, and inside those autonomous systems, we'll find the most frequently appearing routers in many through several trace routes. We try to identify the most frequently appearing routers in that particular location. And then we did also some thought experiments, not real experiments, but to see what can potentially be the impact of a bigger form of censorship, such as BGP prefix hijack attack. Apparently, there have not been too many instances of those worldwide, just a few, but I believe there was one in Pakistan in 2007 when they were trying to block YouTube, and they advertised a prefix so as to they advertised a prefix, a longer prefix to YouTube. As a result, because of your longest prefix match, a lot of internet traffic was black holed into this is black hole, so that and as a result, what happened is that it attracted YouTube traffic from all over the world, and YouTube was inaccessible by anybody else, even outside Pakistan. So how YouTube fixed it back then was by installing even a route which was even shorter than, or rather even a more longer and more specific route compared to what they had. So that's how they had restored their connectivity back. So the other one was, I believe, one in Russia in 2015, but we haven't seen much of such kind of happening very frequently. Second. Something wrong. Okay. Yeah, sorry. So the internet really, before we move it, how does the internet really look like? As I said, this is hierarchical structure. So in this figure, you are seeing these nodes. These nodes represent these A's. These are A and D in this figure. This top figure, A and D are actually customer A's, like you and me, like most of us. Yeah, we pay to our ISP to get connectivity. The money flows in this direction, but so money flows in this direction, and so what B is the provider. B takes the traffic of A, will send it to, if it is sent to D, it will send it to the provider of C. C will send it down to D. Between B and C, oftentimes there is no money exchange because these are what are called tiers. So the tier 1 ASs are actually peering. They're actually, we call them having peer-to-peer relationships, while the customer to provider is generally called the customer to provider, or P2C or C2P relationships. Right? You cannot have, so this is basically called value tree routing. You can't have something like this, the bottom figure. This is invalid. Why? Because here I is paying to E and G, and the traffic from E to G goes via I. This can't work, right? Because I is anyways paying to E. I wants E to send traffic to, why should I send traffic back to I? Why should E send traffic back to I? So these internet relationships, these internet relationships are already, so there's already an algorithm for identifying these internet relationships by looking at global BGP routing prefixes. In fact, the same author, Lixin Gao, along with her colleague, somebody called Chu, they came up with this algorithm to create AS level paths from everywhere to everywhere based on those routing table entries. How this really works is, then I'll go just briefly over this, is that let's say you have, how does a routing table entry will look like? How does a BGP routing table entry look like? You have a prefix followed by a list of ASs. Like for example, this prefix followed by 3, 2, 1 prefix. Now, from 1, it wants to extend a path somewhere else because it doesn't know it's trying to do it. Basically, if it's trying to create a map of the internet, it has to extend some paths to some sort of a depth first traversal. So you're going to that's exactly what it does. It does a depth first traversal. So how does it do a depth first traversal? It sees that 1 has these different tiers, 4, 5, and 6. It knows. So it's going to look into routing table entries across in the entire set of routing table, what we call the ribs, BGP ribs, and identify cases where 1 and 4 are connected, and where 1 and 5 are connected. So more the number of connections between 1 and 4, higher what is called this uncertain, higher what we call is certainty. As the lesser the connectivity, the higher the uncertainty. So how do you select? How do you extend a path? You would want to choose the shortest possible path to a target. So one is the shortest path selection. The second is minimum uncertainty, right? So as I just said, you look into the routing table entries to identify, to find the frequency of these connections, to identify whether should you extend it or not. Turns out that from our study, it looked like that just about 8 ASs cover paths to almost 99% of open DNS resolvers in the country, which also includes your 1.1.1 and 8.8.8. Not only that, we also saw that we also use the same AS level, that same AS level map, and we identified that about 3 or 4 ASs together, they capture 90% of the traffic from all Indian customers to popular websites as well as sites which are likely going to be blocked. But we didn't have a list of sites which are going to be blocked, so we use various known lists. Like for example, we use Herdic and we use um, the so there's Herdic. There's also there's one from forgetting the name. This is based out of it's based out of Harvard. I'm forgetting the name. There's a group which actually looks at um, mm, yeah, sorry. So we use Herdic. We use the freedom of speech index to identify popular websites which are actually being filtered. So from that, what we did is we identified these ASs which appear most frequently in maximum null paths. So it turns out, as I said, 3 or 4 ASs capture almost everything in the country. Right. So you have 3 of ASs capturing almost everything, and and as I said, about 8 ASs capturing 99% of paths to all TNS resolvers. That actually should make you worry. And not only that, we did this simulation of a BGP prefix hijack attack. It turns out that any one of these, so back then there were about these top 10 ASs. Now even the few of them have even gone out of business. So back then, any one of these ASs could go and disrupt could do a fake prefix advertisement, and that could go and censor almost all the Indian ASs back then. So one AS was sufficient to censor all the Indian ASs then. That's primarily because of the hierarchical nature of the internet structure. Not only that, it's also going to impact non-Indian ASs because a lot of traffic originates outside the country, because the customers of the popular ASs in India, the popular ISs in India, the customers are not only Indian but are also non-Indian. So it also has non-Indian customers. So the key insights were with that, very few ASs intercept almost all the DNS level paths, and just both for DNS and important website. And as I said, just one prefix could have been, one prefix was just sufficient to really really hijack all the prefixes. But the thing is, here we did not have any, so anyways, so the likely types of censorship which we were studying back then was one was, which we generally believe, this is what we generally believe also in the community. This is the kind of censorship which people have. BGP prefix hijack attack, which we kind of conjured up. We haven't seen too many instances, but that we know has actually has been used at least once. TCP IP header filtering. This is what people would very often believe, that if you want to block a website, block its IP address. The problem is you could do that, but that makes it difficult, firstly, for identifying for an end user whether the site is just not is it just unavailable or filtering is happening. We'll never know. Secondly, there is IP address bigger problem is IP address localization due to content delivery networks. Now, content delivery networks bring content closer to customers by deploying these edge servers. Now, with CDNs, you have an interesting phenomenon called anycasting, where one IP address is advertised through many at many different locations. So the same IP prefix, which advertised in many different locations. If you want to, let's say you want to block google.com, believing that you'll block access to everything to google.com, that you're mistaken. You may be only blocking google.com in your vicinity, in your local area, not for everywhere else, not for everyone else. Second is DNS filtering, that is the server responds with incorrect IP. So we'll talk about this. This actually happened. But were we missing something? We didn't have actual ground truth back then. What was really going on? It turns out what we saw that from these ISPs, what we did is we tried to, so we did not have any list. As I said, we did not have an official blacklist. We created one based on the various sources. And it turns out that there was no uniform censorship. Now, somewhere, for example, like BSNL and MTNL, which were really government run, they were really censoring a lot of traffic. This red one, the censor one. While those like Airtel and Sifi, which are private players, they are barely censoring anything. And as you can see, primarily the most often what these ISPs by and large censoring was primarily pornography. So we thought, okay, fine, let's take a closer look at how this really works. So this actually led us to our subsequent work, where we try to see that what sort of content is censored, how it is censored, what triggers the censorship, the coverage and consistency, that means the efficacy of censorship, loopholes and evasion, right? So back in 2018, and even now sometimes you will see in India, every time somebody accesses a website which has been blocked, you see a notification, something like this, that it says that the requested URL has been blocked as per regulations from Department of Telecommunication, right? So this is what we call, that's one very easy way to identify whether it's been censored or not. However, a lot of times censorship does not even, it does not give any kind of observable, it does not provide any kind of observable phenomenon as well. I mean, you may not see any notification, nothing that can happen. Okay, so right. So since we did not have the two major challenges we had was that we did not have any official block list. Secondly, censorship became employed where ISPs were undisclosed. So what we did is that we filed an RTI back in 2017. So what's an RTI? RTI really is what's called right to information, where a citizen can file an RTI against to any government body and ask, and solicit information regarding various things. For example, so what we did is we filed a RTI to Ministry of IT and Telecommunication, asking them how exactly do they censor traffic, what do they censor, and how do they censor. And this is what we got as the answer. As you can see, this is written in very complicated language here. Doesn't say much, so we had to actually sit down, read through the fine print. We understood this is what it roughly means, that we will censor something which we will not tell you what we'll censor, and we leave it to the ISPs to figure out how they want to censor it, right? So thus we curated our own list of what we call potentially blocked websites. We don't know if everything of that list is blocked or not. So in this list, what we did, we curated 1,200 websites from various sources. There was Citizens Lab, there was HERDIC, and various past government orders. They were organized into 7 of these major categories: escort services, pornography, music, torrent, politics, anti-censorship tools, etc. The first approach, the first thing which we just mentioned earlier, is that the first method which anybody might be thinking about for censorship is TCP/IP filtering. Turns out that never happens, and we actually tested that. We could not find a single instance of TCP/IP filtering. In all these cases, the regular TCP handshake actually worked. So that showed us that, hey, if somebody has to block with TCP/IP filtering, it should block exactly at the connection level. It should not happen later. So one particular kind of censorship is kind of ruled out from that list. This brings us to the second kind, which is DNS filtering, right? So what we did is, from these potentially blocked websites, we went to this list of blocked websites. Now, one potentially actual list of blocked websites. How do we do that? We use this basic heuristic where we discovered that what happens is, for DNS-based censorship, really, what are the possibilities based in what we try to see what kind of mechanisms are used in the literature for DNS censorship, and we also try to see the same thing in our case in India. We observe that whenever we are accessing whenever we try to resolve the name for a blocked website, 2 of these things generally happen. One was either you get a resolved IP address which belongs to the same autonomous system as the client, so you get back a strange IP address of the same as the client, or secondly, is that you get what is called a bogon IP. Those IP addresses which are really, there are this list of IP addresses in the in the entire range of IP addresses. There are those which we generally reserve for private networks. Okay, any particular packet destined to any of these private addresses should generally be discarded as bogus IP address, basically bogus targets. So these are 2 heuristics we applied to identify whether the site the site was likely being blocked or not. And on top of that, we actually manually went ahead and checked which ones were really blocked. So it turns out that out of about 1,200, around, oops, again, the screen froze. Okay, it turns out, second, It turns out that from around this number, so from around 1200, we went down to about 800, 900, which were actually being blocked. Okay. So, but as I said, so how does DNS censorship really work? There are two mechanisms by which it works. One, what is called as DNS poisoning, where the DNS resolver is going to send you that bogon IP address or IP address of your IP address that is corresponds to some IP address in your own autonomous system. The second is what we call a DNS injection. So what is DNS injection really? It's that it's not the DNS resolver which will do it. It's somebody in the middle, deliberately positioned, installed, so that it's going to respond with a fake DNS response. That's called a DNS injection. So we didn't know whether this DNS filtering was happening due to DNS injection, or was it happening due to DNS poison resolvers. So what we did, we devised a technique called iterative network tracer. The idea has been derived from traceroute. So in traceroute, as you know, you send UDP or ICMP messages from a source to a destination with increasing TTL value. Here, what we did, the client sends out a DNS query to. So here the client is the client. The destination is the DNS resolver to which the query will be going to. The client sends out a DNS query, but it sets the TTL to be just one, so that in one hop it expires. Definitely will never make it to the target. Next time it's going to send it to 2, 3, 4. At some point, it might encounter the DNS middle box, and for that it might get a fake response. Or it may never happen. It may you may have to actually go on increase the number of hops as long as you don't actually reach the target destination resolver, and then that case what we call in that case we conclude that it is actually a poison resolver which is doing this for us. Okay, so next slide. Okay, so turns out, how did we then, based on this, how did we actually measure? So we needed a metric to measure this efficacy of DNS censorship. Again, among the 7, 8, 10 ISPs, the top 10 ISPs back in 2018, we had discovered that just 2 of them, the government area, MTNL and DSNL, are the ones which are actually doing DNS censorship. And it turns out that both of them, they were back then using only poisoned DNS resolvers. From this list, we identified what we came up with 2 metrics. One is called coverage, meaning what fraction of these DNS resolvers are poisoned, and the second one is what we call as consistency, which is that for every blocked website, now from PBW we have gone to a BW blocked website, we determine the fraction of poison resolvers which are actually blocking it. Right. It turns out, as you can see from the figure, it looks like MTNL particularly is, it has a higher consistency, meaning it generally. So as you can see here also, in MTNL the coverage is about 85%, meaning 85% of the resolvers have these capability of sending out fake DNS responses. Well, BSNL, the number is much lower, but you still have this for 9.3% here. And no wonder you also see a very similar consistency metric back then, meaning as I said, the number of websites which are blocked by these individual DNS resolvers, a fraction of those. For MTNL is much higher. For BSNL is like really low, under 10%. Okay. Then comes HTTP censorship. Now,
Sambuddha, in the interest of time, maybe you can wrap up in the next 2-3 minutes.
For 2-3 minutes, I have a lot of content.
You have a lot of content. Okay, maybe I can give you how much more time do you need?
10-15 minutes more.
10-15. Okay, let's do 10 minutes more.
All right, sure. I'll try to wrap it up quickly. So I'm sorry for the thing that's going too slow. So the idea was that we identified how exactly. So we looked at DNS censorship, then we thought of looking into HTTP censorship. For HTTP censorship, it turns out we captured the traffic and we identified here, as you can see from the figure, that every time you access that particular, whenever you saw that notification, you were actually getting in the payload, you get this particular URL, and this particular URL hosted on airtel.in is actually the same page which shows that this particular website has been filtered or blocked. Now, wait, slide, okay. Right. Right. Stuff. Okay. Turns out, not only do you get that notification that this particular site has been blocked, you also get the actual notification from this blocked website eventually. But by then, the connection has already been terminated. Now, why has it been terminated? Because when you got that notification, second, yeah, when you had that notification, the flag, as you can see, the fin push and apps flags are set here. So it's kind of forcing the browser to disconnect. Okay, we discovered basically two kinds of middle boxes. One was what is called interceptive, where you actually, it's like a trans proxy which blocks the website, and you get a 200 OK with the block message and a fin and push to force you to disconnect. The other is basically what is called the wiretapping, which is very prominent. And also in China, this is what happens over there. So the wiretapping middle box really intercepts your traffic. At some point, basically, it's getting a copy of your traffic. It does not intercept your traffic, it gets a copy of your traffic, and then it makes a decision. So for a blocked website, the website actually, the request is not dropped. So the website actually sends you back the content. But what happens is, moment to send to the block website, the censorship middle box, gets a copy of it and sends you back again the same 200 OK with fin and push. This will force the browser to disconnect from the website. Right? By the time the content, arrives on the website, there's already this, connection termination initiated by the client browser. So, so what really triggers the middle box? We identified for web, it was primarily the host field of HTTP headers. Again, we used here the same iterative network tracer to identify, where these middle boxes are in which ISP. And I'll not go into too much details of this, but roughly I'll talk about the results which we saw. We saw that 3 of these areas, like Airtel, Vodafone, and Idea, which were actually not doing DNS censorship but HTTP filtering. We saw that for Airtel, for Idea Cellular, which is now Vodafone, the consistency, that is means that if you have discovered a middle box, what fraction of websites does it really block? It turns out for Idea Cellular, the consistency was pretty high. As you can see, also the coverage was high, both consistent coverage were high. However, for the newer, back then, the new ISP in the market was Jio, which was basically the distant, Reliance Telecommunication. That at back then was not really filtering much, so barely, its coverage was 6.4, and like on an average, it was about, like when we measure from outside, you could not measure from inside, that is outbound traffic, about 6.4% of the network paths were actually having a middle box. Some like Idea and Vodafone were actually using an interceptive middle box. So so evading was not hard, but DNS censorship, all you need to do is use a public DNS resolver. For web censorship, as I said, it is the host field. Now, if you just fudge the host field, it kind of works for both interceptive and wiretapping. So that simple. You do not require a VPN, a proxy, or anything like that. Right. This brings me to the second part of it, is what is called the TLS censorship. Now, in TLS censorship, HTTP censorship, the actual HTTP packet is completely encrypted and not visible. So how does the middle box really, do the censorship? So we are seeing this since 2020. So what really turns out is that the client hello message in a TLS handshake has what is called the SNI, server name identifier. This is matched with the certificate. So this is what the web server looks at for sending the appropriate certificate to the client. So this turns out this is generally the domain name. So they are actually blocking based on this one. Right. So as I just said, the client hello is ABC, you get a certificate from ABC. Similarly, if the client hello has an SNI PQR, you get PQR certificate. That's how it works. So what we discovered, again the same kind of things we saw. We still see wiretapping and intercepting middle boxes. Here now, the just that moment it sees, so it is now triggered not with the client. It does not get triggered with HTTP GET request, but during the TLS handshake phase only gets triggered. Right. So now the two ISPs, Idea and Vodafone, they have merged into one single ISP called Vodafone. They earlier, so back in 2018, they were mostly using wiretapping middle boxes. All of them were using wiretapping. Now in 2021, you see two of them, they have started using interceptive middle boxes for both HTTP and HTTPS, while Geo continues to use the same wiretapping middle box. And this is roughly, now you can see the number of the number of websites blocked by all these is roughly, pretty comparable. But the interesting catch here is for Geo, as you can see, that they're just about 7%. So just about 7%. This number means that just about 7% of these middle boxes, they filter about 21% of the block webs. And I'll quickly tell you why this is happening, really. This is some results of DNS. So now we also are now not only, so earlier we were seeing MTNL and BSNL, now like MTNL has gone out of business. BSNL, it is very hard for us to now even get a new SIM from BSNL. We could not even try that. But what we know is there's a new player in the market called ACT Act Telecommunication. This is a new IS in the market. Back in 2018, they were not doing any censorship. Now they have both DNS injector and DNS poison resolvers and injectors, both of them. Where injectors are much more effective in censoring the traffic. So what was the interesting phenomenon I just mentioned, and I spoke about this in the beginning, was we discovered that along paths to the unblocked websites, if you now send a request with that of a blocked domain, you do not see any censorship. But on the paths to the blocked websites, you observe censorship only if the request goes to the blocked website, where the domain also is the web blocked website. But if you send the same request in the SNI field to an unblocked website, you never see that censorship problem. Yeah, your handshake might not work because it's a wrong SNI, but it's never blocked and blocked. So that kind of tells you, this kind of gives an idea that now slowly, because of the nature of hosting, few autonomous systems are actually hosting large fraction of, few ASs are hosting large fraction of these the sites which are blocked in the country. The last part, I'll try to quickly wrap up this thing without, I know I'm running way out of time. I'm really sorry for that. I'll try to wrap up this quickly. So as I said, back in 2020, the government blocked 220 apps through a series of various, notifications and declarations to the public. So our initial observation, as I said, out of the 220, 60 were just unavailable and defunct. Okay, we just not find them. We obtained 160 among the remaining 160. We found 136. So the remaining 160 we obtained the APK from various foreign sources and APK sites like APK Mirror, etc. Of those 136, where once you install the apps, again automatically it starts working. Turns out that there's 24 of these apps which are not being, don't know much about them. So what we discovered, I will not go into much detail. We discovered that 16 out of these 24 apps are actually filtered by the CDN edge server. Now, even if you try to connect to a non-Indian CDN edge server, that looks at your source IP address and blocks you. So that means these companies, they are complying to government coercion, which is very strange because they have been kicked out of business. And so this was across all CDN resolvers, even if you, CDN edge servers. So regardless, these edge servers were in the country or outside, everywhere using this. How did we get to resolvers outside? It was not very difficult. We chose resolvers outside the country, let's say in a foreign country, which is relatively uncensored country. And so automatically you'll get the IP address of a edge server, which is in that target country. There were still 8 of these remaining. Now, for that, we still did not have an answer from this. So we thought, okay, fine, must be something else going on. So what we did, we took the app, we analyzed it using a setup where we did an MITM on the app traffic to inspect what goes on and how does the server identify. Turns out that really, and also we also had to reverse engineer some of these apps, and we chose, in this example, we're talking about TikTok, which had about 2 million followers back in 2020. We identified that in your that in the several requests which go from a user in India, several of them, they bear this 2-letter country information somewhere in some plain text information, somewhere in some header. particularly for though it's encrypted, but it's there in the header. So when the target receives it, decrypts it, identifies where it is coming from. It turns out that really there is, after reverse engineering, we identified that there's this particular function called get sim country ISO, which really probes your sim to identify the carrier region, right? So carrier region equal to get sim. So this is kind of this function. This carrier region gets your actual country information. Now, all you had to do is either you bypass this in the bytecode, or if this carrier region field is replaced by IN is replaced by anything else, it will simply work. Or an easier solution so that nobody has to do this reverse engineering, etc. Just take off the SIM, use the Wi-Fi. Even that works. So that's straightforward. It took a while to get to this, but this is what we discovered eventually. Yeah, I think that's pretty much it. Sorry for this longish presentation. It went ahead longer than expected. I'm willing to take questions from the audience now.
Thank you, Professor Sambuddha. That was a very interesting talk, and you gave a quite extensive overview of the different taxonomy of censorship techniques and the different ways operators are actually actioning those censorship. You talk about also the different routing incident that happen, and also how networks are prone to hijacks, and this is why it is important that network implement the best practices such as routing security, whether it is RPKI or other type of filtering, the use of DNSSEC, and also maybe encrypted DNS can mitigate a little there's
a catch over there. Like, right now the drive is towards, I'm pretty sure you are aware of DOH and DOT department. Sorry, DOH being DNS over HTTPS. The catch is, you have DOH, you have DOT, you also have now the ECH header from Firefox, which they're talking about.
Right.
The problem in all these mechanisms that you can still identify that somebody is using them, because DOT works on uses a specific port number. And I think this is 857 or something like that. You can identify those easily. DOH will then require you to go to a DNS. So it will require you to go an HTTPS site and get the DNS query. But how do you then reach that HTTPS site then? Maybe you need another DNS resolver for that, or it is a fixed IP address. If it's a fixed IP address, then it's very easy to identify.
Indeed, the payload might be encrypted, but still the headers are still clear, and then censorship can still happen even with
And blocking ECH is like blocking ECH is like almost trivial. So in case of ECH or ESNI, Cloudflare already implements ESNI. How they do that is you have to send a TXT DNS query to a specific. So if let's say it's a site which is on Cloudflare. Discord.com is on Cloudflare. So if you take the domain _esni.discord.com and you send a TXT query to that, you will get back the public key, which you will use for encrypting the SNI. Now that's fine, so far so good, but it's pretty trivial for the ISP to just look at, just not allow you to send TXT queries.
Exactly.
It does not break anything.
Yeah, it doesn't break anything, because who uses TXT queries?
Who uses TXT?
Yeah. Great. Do we have questions from the audience and also from the panelists? Yeah. So Hannah, you have a question. You can ask your question.
Yes, hello everyone. Thank you, Sambuddha, for the great presentation. My question is, how do you tackle the issue of false positives in such measurements?
Good question. How do you tackle false positives unavailability? So right now we don't have any way to do that. I mean, there are these tools. For example, you have Uni. Uni can be used, but problem is Uni itself has a lot of false positives in its false positives and false negatives in its results. Reason being, they have not yet updated their heuristics for identifying what is blocked and not blocked. Like they generally do it for HTTPS filtering. will compare the page contents. Now, page contents can change across different locations based on localized advertisements, language localization. These things can actually change. If you access Google from, or if you access any particular Amazon from 2 different locations, you may get a different page altogether based on the content. So that automatically will be flagged as a censored website. Right? One is that there's a problem with that. Second is, in our case, we actually went ahead and did a manual inspection to check whether they're really blocked in the country or not. We had no way to we had no automated way to identify false positives in the studies. And then this is an open problem. This is an open problem in the community. We still don't have answers to fully say how to identify whether it's really censorship or disruption, etc. Still, various levels we don't know this. And even for internet shutdown, there's a project of Qaeda called IODA, which really looks at internet disruptions. Now, whether there is a disruption, whether it's shutdown, there's still no clear heuristic.
Maybe I have a question for you, Sambuddha. So what type of measurement systems are you using to, for example, to detect middle boxes?
Right. So we were, as I said, we created this own tool called INT, Iterative Network Tracer, which is basically a kind of a glorified, you may say it's a glorified trace route. All it does is you first do let's say you want to identify the web censorship. You first establish a regular, so a particular domain which you want to check is blocked or not. What you do is you first make a connection to a domain which is is not blocked, or your own vantage point somewhere. You connect to that, your own, say, let's say cloud VPS. You connect to that. Once you've made a connection, you send out, once you've done the 3-way handshake, after that you send out the HTTP query with increasing TTL value. Now the query will have the host field as the block domain, or in case of HTTPS, it will be the SNI field will be that of the block domain, because we believe that the middle box is actually looking for plain text information in the SNI or the host field, and it does a basic string matching to identify whether this packet, the request is going to the block domain or not. Really, they don't look at IP addresses; they look at maybe the block domain, because you could connect to a block domain. Sorry, you could connect to an unblocked domain. You can even connect to a block domain. The 3-way handshake really works. The censorship is triggered in HTTP only when you see the HTTP GET request, the first GET request, or if it's the first TLS client hello. So only then the censorship is really triggered at that point. And so what is really plain text at that point? In one case, it is the host field. The other case, it is the SNI field. So that's what we did. We crafted these requests with increasing TTL values. We used a Python's KP library for doing this. These got detected, and once you get detected, you get back the censorship notification. So it's really a kind of glorified trace route, you can say.
That's interesting. Have you ever studied any sort of BGP type of filtering techniques? I know some applications that let's say regulators can ask network operators to install some application that would actually inject very short prefixes, like even /32s to redirect traffic for the IP which are supposed to be blocked. Have you actually studied that?
I have not, and I would want. It's a very interesting, pertinent point. I have not, and I actually would want to, look into that kind of problem as well. If whether ISPs do that, how can they do that? What will be the bigger impact? Can they really do that? Like, for example, if you want to block 8.8.8, if you install a /32 prefix, how many ASs will it really impact? Will it just impact the target ASs, or there's going to be a lot of collateral damage?
There was an incident in Mauritius where some operators were doing that type of filtering, and there was some child sexual abuse material. It was apparently hosted on a Cloudflare network, CDN, and the fact that they blocked that IP to Cloudflare, many other content, like legitimate content, couldn't be accessed as well. Yeah. Interesting. Thank you, Sambuddha. So if we don't have any more questions, I would like to thank you very much for this interesting talk and keynote speech. And please stay around for Q&A session at the end.
Definitely.
And we will now move to our next speaker, who is Anurag Bhatia from Hurricane Electric. He's a network researcher at HE, and he operates a global backbone spread across North America, Europe, Asia, Africa. And as part of his job, he likes spending time analyzing routing, optimizing routing, and playing with BGP. Anurag, welcome, and over to you.
Thanks for the introduction, Amreesh, and thanks for this opportunity. So, good morning, everyone. I'll be talking about Indian traffic getting routed from outside of India. So let me start by sharing my screen. There we go. Amreesh, can you please confirm if you can see the screen?
I can see it.
Okay. So I'm going to skip the background since Amreesh did a fantastic job on that part. So a quick background of this talk. This started from one of the blog posts I wrote a while ago about Indian traffic appearing to be routing from outside of India, and the case on why it was happening that way, and the possible issues with that. So Amreesh picked that blog post and reached out to me, asking if we can convert this into a talk. So essentially, this whole presentation is based on that blog post. I've linked that blog with the slides, and I'm going to share the link to the slides after I finish. On the basic understanding so that everyone is on the same page with respect to what the setup should be like, so that one can understand what an anomaly looks like. So I think Professor Chakravarty did a good job on his presentation there. He talked about very basic fundamental parts of the peering and interconnection. I find his talk excellent with respect to how he looked for the applications which are blocked. Although I personally totally disagree with the content and the views on complicated topics like, say, Kashmir, where it's just hard to discuss those topics in absence of background and history, etc. So it was good regardless on his introduction. So I'm going to carry forward on the topic which he introduced on the peering part. So how BGP works? You can take BGP essentially is the border gateway protocol. It's a signaling protocol where routers signal to other routers, telling that which route they know and how to reach there. It's the only option where it's the only protocol you can essentially use between different networks, essentially called as AS, autonomous system. So an autonomous system is just a network which is autonomous in itself. It can has its own routing policy. It can has its own IP addresses. Its own decision making, who it want to connect to, who it want to does not connect to, etc. So router essentially speak BGP with the other speakers, and it's often called as adjacencies, or often also called as peers. So networks peer with each other, and they exchange the route. Adjacency relationship can be different based on the commercial setup. So an adjacency can be a simple settlement-free peer where routes are just exchanged without exchange of money, where essentially a network promises the other network to carry traffic to its customers only, and same with from the other network. While the other case can be where this sort of adjacency setup can be commercial based, where a network promises transit to another network, where it give it guarantee that it is going to carry traffic nowhere, no matter where the destination it is going to take it to. So key element which are shared in this is often prefix, next hop, and the AS path. This is the classic dark theater example I often use in workshops to explain BGP. So imagine you are sitting in, you have gone to a theater and with a bunch of your friends, and suddenly it goes all dark, and everyone is sitting at different locations. How would you find who is sitting where? And imagine this is not the case with only your group; it's the case with almost everyone else. So you got a few hundred people sitting in a dark room. Now, in order to build it up, one way can be a single person goes to each table and just records that. But then you have a single point failure. That person may fake something. The person may take much longer time. Another more effective way can be you pass a paper to the first person on the first row. He just writes his name and then passes the page to the other person. The other person says, the person 1 is sitting on my left side and I'm person 2. Then it goes to person 3 and so on. And the page is just floated across the room. Within a few minutes, you'll have essentially built a table where you know who is sitting where and now how you can reach those based on the path you have received. That's essentially how BGP routing works. Once you understand, once you include the fact of the tier 1 network in the transit-free relationship, this is essentially how the internet is built. So you may come on this question, how ISPs guarantee global reach? How, say, an ISP in Hyderabad or New Delhi or Haryana, where I'm sitting right now, can guarantee global reachability to some network far away, say some network in Chile, some network, say, in Russia, some network, say, in some far away place, say, South Africa? Well, it's based on the transit-free tier 1 network relationship. Advanced warning, it's a quite abused term. So whatever you have heard about tier 1 networks so far, probably you should forget it, excluding what you heard from Professor earlier, which was quite on spot. So essentially, a tier 1 transit-free network means that it is transit-free. It does not take transit from anyone. So it does not essentially buys internet capacity on layer 3 as in transit to reach any place. It can reach all networks in the world either because they are its direct customers or they are customer of its peers. So it's not buying transit from anyone. Approximately 15 networks globally are considered to be tier 1. The list varies on IPv4 and IPv6, and you can find usually the Wikipedia entry is mostly up to date. Some of the example includes AT&T Autonomous System 7018, Verizon, GTT, CenturyLink. From India, on the Indian context, you have Tata Communications, which is considered to be a transit-free tier 1. All transit-free network peers with each other, and they do not have any transit, so they must peer with each other. If any of the transit-free network, happen to de-peer for any technical or non-technical reason, there's going to be a black hole between those networks. So that's essentially by definition. So everyone on the internet is a direct or indirect customer of one or more of these transit-free networks. So when you go on the context of routes going from outside of India or routes being unoptimized, essentially you have to understand that unless it's multiple transit-free network having issues, if it's a non-transit-free network, there are always going to be a route between them just through an unoptimized path, which could be far away, which could be from a point far away from here. So there's always an alternative route, except when it's between tier 1 networks. If in this list, if say for instance AT&T and Verizon, if they somehow break their relationship, there would be absolutely no path. Customer of AT&T won't be able to reach customer of Verizon, for an example, in such a scenario. But if say any of the non-tier 1s, say in the Indian context, say BSNL is not a transit-free tier 1, and say Jio or Airtel are also not a transit-free tier 1. If they break peering relationship, there still would be a path, because both of them have to be customer of one or more of these tier 1s, and tier 1s ultimately are peering. So there's always peering somewhere up that transit chain. So that's on the basic context setting on what you should expect when there is an unoptimized path. Then we can go on the Indian peering ecosystem. So what the Indian peering ecosystem looks like, how networks are connected on that part. So who peers with whom? Well, advanced warning, this changes quite often. So whatever I have written here is quite valid till today. I can't guarantee whether it would be valid tomorrow. So key players by size, volume, routing table are essentially, as you can imagine, Bhatia, Airtel, Jio, Vodafone Idea, BSNL, Tatacom. Reliance flag, not so much these days, but it used to be an important network. It still is a quite important network considering the submarine cable assets, etc., and other things. Then Telstra and Sifi, relatively smaller in India, but still Telstra is quite large ISP outside of India. So these players connect to networks outside of India. There might be some network which I might be missing here, but essentially this covers almost all, maybe 99% of the networks which connect outside of India. So all networks are essentially downstream customers of one or more of these networks. If you look at the AS numbers, there are somewhere around 1,800 to 2,000 autonomous systems active in India at this point of time. This includes autonomous system numbers of data centers, ISPs, RBI, even institutions like IITs and some of the NITs, etc., and most of the banks as well. Key internet exchanges, Nixie, ExtremeIX, DECIX, M6 SIFI, etc. Typically, large networks do not peer at any IX in India except Nixie. That's by design so far. They are following a close peering policy inside India, and they would typically peer at Nixie because they were asked to peer earlier. And they would announce regional routes only at Nixie. Why I'm mentioning this? Because it becomes important when I jump onto the results in the third section of this slide on the unoptimized routing. So what does regional route announcement mean? Essentially, one of the policy in Nixie says that if you are connected at Nixie, you must announce your regional routes, not all their routes. So if I am a network connected to, say, Delhi, Mumbai, and Chennai, and I have presence in Delhi, Mumbai, and Chennai, essentially I'm required to announce my North Indian routes at Delhi, West Indian routes at Mumbai, and South Indian routes at Chennai. Not the complete table. And many of the network follow this policy very religiously somehow. So that's one of the reasons you'll find regional routes only, and it creates a lot of issues around asymmetric routing and many other challenges at Nixie. Other than that, ExtremeIX, DECIX, they are quite large, good, big exchanges. Lots and lots of content players peer with lots and lots of ISPs, excluding the top, 3 or 4 ISPs. And these top 3 or 4 ISPs, they carry a very large customer share because there's much lower deployment of fixed line. There's extremely high number of mobile internet users. If I'm not mistaken, that's probably second largest, after China. And although the number of fixed lines is increasing quite fast, but it's still so far the case. By design, one can expect to see Airtel, Jio, and Tatacom to be reaching all other Indian networks directly. And so many times people often refer to them as I said, the bad marketing terms, as regional tier ones or the Indian tier ones. Essentially, all Indian networks are customers of Airtel, Tata, or Jio for most part. There are certain exceptions there, and that's where you can imagine if there is a broken peering between these players, you can have serious problems. You can have lots and lots of traffic escaping India. Some networks which have significant presence outside of India but typically rely on their own backbone. This includes networks like Vodafone Idea. So it's as many of you know, Vodafone and Idea are separate companies. They're merged together, and Vodafone is quite large globally. They also acquired Cable and Wireless. So it's Vodafone Cable and Wireless AS1273, which has large presence outside of India. And Vodafone Idea essentially relies on that for most of its internet capacity from outside of India, but it does rely on Indian networks to typically reach Indian networks. This also includes networks like Telstra, which is mostly a transit network. They don't deal with end customers. They stay as a transit provider for network providers, and also SIFI. So SIFI also operates a backbone, essentially peers with networks outside of India, and heavily relies on Nixie and some other interconnection and peerings, along with its transit relationship with Tata to reach Indian networks. So that's broadly the larger Indian peering ecosystem. Does it matter a lot? Well, it matters when you start analyzing routing with large players. If you start analyzing the traffic based on the volume part, then it does not matter that much, because as of now, a lot of traffic flows from large content players towards eyeball networks, and there is good connectivity from large content players all the way from Google, Facebook, Netflix, Amazon, all the large guys with most of Indian networks. This includes the large as well as the small, as well as the mid-size ISPs. So by design, all the traffic should stay within India, as per the design I just mentioned in the ecosystem slide. That should be the case, but that's somehow not happening. Let's understand why that's not the case. So here's one of the example. This is a case where I'm tracing from to a BSNL IP address somewhere in South India, essentially in Tamil Nadu, from one of the Airtel connections. This is utilizing RIPE Atlas probes. So one of the probe on Airtel is tracing. We see the traffic at Airtel gateway. Let me just turn on my laser pointer. It would be easier to do that on screen. Turn on laser. Okay, here it is. So Essentially, third hop is still India, fourth hop India. Then suddenly we find from fifth hop onwards, the latency jumps heavily. It should not matter much if it jumps only on fifth hop, but we see a consistent jump from this point onwards. It goes all the way from 50 milliseconds all the way to 270, 260 millisecond range, which tells you that traffic might have leaked outside. Another clue here that traffic has leaked outside is the seventh hop, which is the IP address belongs to AS174 Cogent, which is this hop is outside of India. You can figure it out by tracing to this specific hop from multiple points outside of India. Plus the fact that Cogent is not present in India, so there's a high possibility that this is going to be outside. So it goes to Cogent and then it comes back. Cogent here is considered to be a transit-free tier 1. So essentially, Airtel is a non-transit-free tier 1 is going to a transit-free tier 1 Cogent, and then some either eighth hop is Cogent or someone else, and then it goes to BSNL, and then the traffic comes back to India. So traffic leaking outside. Okay, let's look at another case. Here's a case where again I'm tracing from one of the probes on Airtel towards in this case the destination is not BSNL, this is Vodafone. I picked the speed test server on Vodafone network in Pune. So essentially the traffic goes to Airtel, then suddenly the latency jumps to 140. 140 millisecond is a remarkable number because you can reach all you can reach the farthest point in India within probably 60, 80, 70, 80 milliseconds probably. Even from Delhi to Singapore is like 80 milliseconds. So I believe probably from Kashmir to Kanyakumari should not be more than 70, 80 or 90 milliseconds. So once you cross this 100 millisecond threshold, you can be sure that if the endpoints are within India, then something is really fishy with routing. If you read the trace route, it is hitting LON 13, which means London, probably 13th router on again the Cogent. Then it hops back to this is 55644, the Idea global network. So it hits Idea, and then from Idea it goes to Vodafone. Essentially, different AS number of the same organization now, and then goes to Pune. So we are essentially going all the way from India to London, and then coming back just to reach this server in Pune. So clearly a case of bad routing here. So detecting the cases of bad routing and looking at the results. So what are the ways to detect maximum number of these cases? I've put a star here because there can always be more cases. The reason I would call it maximum is because I try to look for all possible cases I could find with hit and try, and try to automate it with scripting to find as many cases as I could to increase this number to find maximum number of such cases. So one way can be look at the routing table snapshot. So there are public route collectors hosted by Oregon Route Views, RIPE-RIS, PCH, etc. Oregon Route Views essentially takes dump over a multi-hop eBGP session with lots of networks across the world. You can take a look at its snapshot to look for certain specific AS path. RIPE-RIS does very similar thing, except that it is, instead of eBGP sessions, this is taking the dump over BGP sessions within exchanges. PCH has a more unique model where PCH takes that dump from collectors deployed within those local areas, usually next to exchanges. And these do not carry the full global table, but a very specific localized exchange and peering view. So again, very, very useful data. Once you combine all these three, it becomes much useful. There are many other collectors as well. So one can look for certain patterns. So there can be certain patterns as, for instance, Reliance Jio uses two AS numbers, one within India, which is AS 555836, and one outside of India. Tata Communications follows again a very similar pattern. So they use AS 4755 within India, then AS 6453 outside of India. 6453 is considered to be a transit free. So technically 4755 is downstream of 6453. So now AS path, if you use this sort of logical mapping, AS path where you see domestic AS of Jio, next international AS of Jio, then again the AS of Tata used outside of India, 6453, and then domestic AS of Tata. This gives you a clear sense that any of the routes with this sort of AS path are extremely likely to be from outside of India. Same thing in reverse, any of the routes, in this case, we are looking at the routes behind Tata, the customer side of Tata. On the other side, you can look for routes on the customer side of Jio, which are learned by customers of Tata. again with this specific relationship in between. Same logic you can follow, say someone with Airtel, although Airtel uses same AS number in India as well as outside of India. But then the same logic can apply if you see 9498 and then 6453 and 4755. You can guess that it's highly likely going from outside. So you can shortlist those cases, look at the trace routes, and figure it out. So that's the way of looking at the BGP table. I built out a list with somewhere like if I remember correctly, somewhere around 20 of such specific patterns to find and sort those cases. Next, you can also do large-scale scripted traces. When you are doing large-scale scripted traces, you have to remember two key points. One, what would be the ideal ICMP endpoint which you can ping? So there can be multiple ways here. One cheap, easy way can be O-class speed test nodes. So you can find host names of O-class speed test nodes, and all those are required to be with open ICMP. This works really well especially with networks like Geo, which are very closed ICMP-wise. So you can't really ping their routers in most of the cases, but you can ping the speed test nodes in those cases. Another way I found was pinging Facebook FNA nodes. So this came out of as a separate project where when I visited Apricot 2018, out of hackathon, it turned out it is extremely easy and fascinating to find all the locations of Facebook FNA, their caching nodes, because they all use a specific string with airport codes in it. So you can run through a list of airport codes in a batch manner and try to find all the strings essentially which are active, and then you resolve those strings with IP address IPv4 and IPv6 and map those to AS numbers, and you can find all those servers. So there are thousands of servers, and all these are not on Facebook IPs, but these are on ISPs IPs, and all these have ICMP open, so they can act as a very good ICMP endpoint for tracing, as well as for ping ICMP test. So essentially one can do large-scale testing against these probes, sort out cases essentially based on latency. So, ping from multiple Indian locations, try to sort with a case like, say, 100 ms cutoff. Anything above 100 ms, look into it, essentially interesting. Then analyzing data based on specific matching patterns. If traffic is going outside of India and coming back, essentially there are going to be a few dozens of IP addresses which it's going to cross to. They are not infinite IP addresses. I'm excluding the content place from this list. So, I'm not talking about if you trace to, say, Google Cloud or Amazon Cloud or Facebook outside of India, but essentially if you are tracing from, say, India to any other network, excluding these contents who have backbones, their own backbones in India, you'll find only a few dozen IP addresses which would appear in your trace. So, whether you trace to AT&T in US, or whether you trace to Telia in Europe, or whether you trace to Orange Telecom in France, or you trace to Singtel in Singapore, essentially only a few dozen IPs will appear on the exit egress side on both on the forward trace as well as on return trace. So you can try to find those IP addresses and then try to sort out the list of trace route to figure out where a trace is taking you. One can cross-validate this data using the looking glasses of the internet exchanges. I heavily relied on looking glass for NIXI because the traditional understanding says that all the key Indian players, they peer together in most cases and in bilateral PNIs. But they also have peering at NIXI. So the traditional understanding says that they would be announcing routes and accepting routes, but that's clearly not happening in the result. So I cross-validated the data just to find whether the route exists or not, to find whether it's the problem of the network responsible for announcing route, or the problem with the network who is supposed to accept the route. So here's the findings. So traffic between Telstra reach AS4637 with POPs of Airtel that goes mostly from outside of India. I attach the RIPE atlas as well as raw traces with the link. You can find the link and open the slides by clicking the links. I'll share the link to slides shortly. Same thing with Telstra and Tatacom routes. Traffic between SIFI and Airtel that seems to be routing from outside of India. I attach the There is a links there. Traffic from Airtel towards BSNL South Indian pools, that's going outside of India. Here the Nixie looking glass become important because it's a very specific case where it's only with the BSNL South Indian pools and not all rest of the BSNL pools. So BSNL in North India, Airtel anywhere, it goes within India. BSNL somewhere in middle of India, say in Madhya Pradesh or Chhattisgarh, again goes direct from within India. But specifically with the case of BSNL in Kerala, Tamil Nadu, etc., it just goes from outside of India because essentially it seems like BSNL was announcing those prefixes, but the Airtel was not accepting at that point of time. Traffic destination to Vodafone Idea, many of these pools is going from outside of India. It turns out they were announcing more specifics to technically their transit provider, which is Vodafone CNW outside of India, and many of the networks are picking those more specifics, and that was the case. I can probably click and show you maybe one or two of these. So here's one of the cases. Actually, I showed you this one in the slides. Let me pick something else. So between SIFI and Airtel. So here you can see this is a trace from Airtel towards SIFI. You can see some of the local hopes, then going to Airtel network 50 milliseconds, then suddenly goes to 7473. That's Singtel, I believe. So outside of India, from Singapore coming back. So I think 120 milliseconds, not that high latency, but still hoping outside of India, not so good thing. So you can find similar cases. So that's essentially on the result side. So why it happens broadly, we can categorize a large number of these cases into these four categories. Not all, but most of them. It's simple misconfiguration. So a network might be accidentally announcing more specific prefix on the international transits compared to less specific to Indian transits. And remember, more specific always wins. So if a network decides to announce more specific to its transit in Singapore or London or New York, then that's going to be the preferred path compared to a less specific, like say /24 on global transits, /23 or /22 on Indian transits is going to cause a problem. Heterogeneous route filtering. This was an old case which I saw. It was fascinating where there are certain networks which are filtering routes based on IRR, not essentially RPKI so far, but RPKI could be a possibility. They are filtering based on IRR, and they are filtering only certain networks. So they are essentially filtering their peers, but not their downstream customers. And that's a quite popular approach where if networks start rolling out filtering, they would start with their peers, gently move towards their transits and eventually towards their customers, because customers where you have the biggest impact. So networks like Tata Communication domestic AS4755, they filter based on IRR, but they filter their peers like 9498 Airtel and networks like Jio, but they don't filter their downstream. So if you are but at the same time they have their global network which is not filtering the customer. So networks like Airtel are being filtered by domestic peer like Tata, but not their international transit 6453 Tata. So this results in these cases of traffic going outside because route is still being accepted. If a route has a bad route object or bad IRR entry or missing AS number in the AS set, the route still would be accepted. It will just cross that tier 1 transit free zone and will come back. Path on which actual traffic flow is not accepted. So in many cases, there are paths, especially if you are tracing towards CDNs. Networks do not tend to optimize it that often. So networks in many cases, they would allocate IP addresses to these CDNs, and now they expect that these IP addresses would attract traffic internally from their subscriber base. And these IP addresses would also be communicating with the network outside of their network just for cache fill reasons. So in many cases, they do not expect that there would be domestic traffic. So say Facebook FNA node sitting on a provider, say somewhere in Mumbai, they're not optimized as such for connectivity with a provider, say Madhya Pradesh, or provider within say Gujarat. They are optimized that their addresses should be visible and should be announced with reasonable redundancy to transit providers in Mumbai or outside of India, just for cache fill reasons. Fourth is lack of peering and interconnection. That's one of the broad part, and probably 60 to 70% cases fit within the fourth category, where it's just lack of peering and interconnection. Because there's lack of peering and interconnection, traffic essentially starts jumping to other level, and then at the other level there's another level of missing of peering sessions. It jumps to the other level. Ultimately, it goes to a transit-free tier 1 zone, and it just it goes from outside of India. So that's broadly the cases and how you can measure it. I have linked the original blog post on my personal blog here. So that's the case. Let me quickly share the link to the slide so you can open the link after the slides. Maybe I stop sharing the screen.
Pasted the link to your blog post as well on the.
Oh, sure. Yeah, let me do that as well.
Yeah.
So if you have any questions, probably do we have time, Amreesh, for questions?
Yeah, we can take 1 or 2 questions.
Okay.
Do we have any from the audience? If you have any, please raise your hand, or please. Oh, we have one. Sambuddha, Professor Sambuddha, please proceed.
Hi, Anurag. This was an amazing talk, and I realized how much more I need to know about this. And I need to read your blogs, and I have to understand this thing. Very, very, very interesting and very related to my work. I have just one question for you. This misconfiguration, be it misconfiguration, be it deliberate rerouting of traffic going outside and coming in back. One question is, how often do we see this in other countries as well, or is it very India specific? We see this other places.
That's a good question, Professor. So the misconfiguration is quite popular outside of India as well, but the result of misconfiguration is not that severe outside of India. I'll tell you the reason for that. If you look at locations like, say, Germany, Netherlands, Singapore, they have lots and lots of transit-free tier 1 networks. So a place like Germany, I can probably count. You have networks like Tata Communications present there, entities over there, Telia is there. So excluding the American backbones which are on last mile, excluding AT&T and Verizon, pretty much every other tier 1 provider is present in most of European countries, whether it's Germany or Netherlands, and same applies even to places like Singapore and Hong Kong. So because these networks are present, even if there is missing or misconfiguration in domestic peering, the traffic is going to ultimately hope from these players. For Indian networks, these networks are sitting far away. So if say out of 15, all 15 networks are present in India and they are interconnected in India, then it does not matter whether Indian networks peer domestically or not. There is going to be ultimately interconnection within India from these providers. That's not happening specifically for India. There is less level also for Asia. So if you look between large tier 1 players, they have excellent peering in US and Europe, but they have suboptimal peering even in places like Singapore. So there are cases where large, you can look at the list of those 15 players where they lack interconnection and peering in Hong Kong or Singapore market, which is still slightly better than India. So that's the case. Misconfigurations are everywhere. It's just that result is quite severe in Asia.
Okay. And so does this have any impact on performance? Like I saw you were testing out speed test sites. And speed test, like let's say if you have a 10 megabit connect, speed test generally in India, you are going to pay your ISP. You have all the right to go and challenge your ISP. Say, hey, you charge me for 10 megabit. I don't see 10 megabit. But by and large, they are smart enough to show you 10 megabit. You get 10 megabit. How does this rerouting and thus the subsequent? I saw that you had the trace route, the round trip time number differences as well. Moment it reroutes out and comes back in, there's a big, there is a big latency penalty over there, performance penalty you might be seeing over there. But why does it not show up in your speed test?
I did not do any speed test as such. I just use the speed test nodes as ICMP endpoints for running scripted ping as well as trace routes, just to sort out cases. I did not do any actual speed test.
Right. But generally, I've seen from my own anecdote. I can again, there's no concrete study on this. But anecdotally, I can say most of the times if you access a speed test site, you'll get more or less pretty much what is advertised by your ISP.
That might be because of the case that there are so many speed test nodes. There's a high chance that you're first going to get a speed test node which is sitting within your ISP. If you are doing a speed test from, say, any of the mobile providers, all of them have localized nodes within your city. Unless you specifically decide to select and pick a node far away from you, you won't see this impact.
Okay. That's all I had. Thanks.
I did very recently saw this impact actually. I was just trying out a different wireless connection, and I was getting excellent speed on speed test, and I was getting really bad performance on VoIP calls. So after looking around, I found that the IP addresses against which I was CG netted, those IP addresses were not announced to all Indian players. So multiple of Indian players were reaching that IP address from outside of India. So yeah, speed test does not mean much, unfortunately, these days.
Okay, thanks.
Thank you.
A question from Romain.
Yeah, thank you, Anurag, for the presentation. That was very interesting. I understand the situation with the tier one. You see, like most of the tier one are not in India, and so that's why things are leaking out outside. One thing I don't understand, though, is why are those networks not peering in India? Why are they not? It's like, it seems, is it like because of the country is too big, that there's too many places, or if you could just comment like on why they don't? Yeah.
I don't think it has to do probably with country. It probably has to do with mostly non-technical business side of things. And many of these networks, even when they peer, they do not essentially peer at all the locations. In a large country like India, you would expect them to peer at least at, say, 10 or 15 cities. But that's not happening. That's what's not happening. So even when I in the list, when I say that these networks are connected, essentially they connect mostly in Delhi, Mumbai, and Chennai. Some networks maybe in rare case, maybe in Kolkata, but that's it. They are not really connecting, say, in cities like Bangalore or Hyderabad or say other key important cities, whether say Lucknow or Chandigarh. So that's one part. Some of it also has to do with what Professor Chakravarty was talking about on the filtering side. So there is a requirement on the lawful interception devices, and it's a very bureaucratic requirement. So when you have to put these devices, you have to work on getting those devices, work with the regulator to set those up. So even if you are present in a city and another network is present in a city, it may not be financially feasible to peer, not because networks are far away. They may be in the same building, but because of these requirements, it becomes sometimes more complex. And in many cases, people don't want to touch it without speaking to. So engineers won't touch it without speaking to their regulatory guys, and regulatory guys would not care that much about latency and performance reasons. They would think on a very higher level of things that, okay, networks are connected at a couple of locations, good enough. Beyond that, I think it is mostly just business decisions, etc. I don't think it has to do with any other technical reason.
Sure. Okay. Thank you very much. It's very interesting to see the difference between different countries. I see the situation in Japan is very different, very different.
So if you decide to. If you pick all IP addresses from all prefixes from Japan and decide to trace out to each of those prefixes, the first IP of each of those prefixes, just out of curiosity, how many percentage-wise, how many do you think would leak from outside?
I think none. Like if you take the big, like you did, like you take the big broadband network, the big IBOX networks, you will see that they are all peering with each other. I think one thing you might see is they are all going through Tokyo or Osaka. There's like some places where all those network meet, but I don't think a lot will go out from Japan. Maybe it's something they also took into consideration because we are on an island. So going outside means like crossing a sea. It's definitely going to take some. Well, going to Europe from India, it's pretty far too.
Yes, that's true. That's true.
A quick question for you, Anurag. There's also a cost factor associated with using transit instead of peering. So is this something ISPs are considering at all, or maybe transit is cheaper in India? That's why that's not so much of an issue.
Actually, that's not always true. So transit being expensive, that depends on where you are sitting in the chain. Excuse me. So, I think there have been multiple feasibility studies being done, and somewhere the number comes like on the transit course, it's like 1:3:10. So at the core, if the bandwidth is somewhere at $1, somewhere in the middle mile it would be $3, and on the last mile it would be $10. So networks who are selling on the last mile, who have significant presence, investment, spectrum, fiber on the last mile, they make a good margin, and they would have lots and lots of control on that element. Now, whether they buy their transit at $3 or $2.9 or $3.9, it's not going to make a big difference as long as they can hold on to their $10 market. If, say, business decision makers, and I personally disagree here, but if, say, business decision maker think that by not peering, it is good to save that $10 revenue, right? They would not mind paying more for transit or carrying it to a location far away. So that's essentially the case. In many of these cases, for large providers, they either have their own submarine asset or they have significant submarine, the significant investment in the submarine cables. For them, if a part of a percentage of traffic leaks out, it would not make a financial dent, although it surely makes a performance dent, and that's where you again have this problem where there is a firewall between the network engineering people and the decision makers in many of the networks.
Okay. All right, thank you, Anurag, because we are running short of time now. Let's move to the next speaker, Romain. Thank you very much, Anurag, who is going to talk about points that was touched upon before by Professor Chakravarty and also a little bit by Anurag, but maybe probably going a bit more in details. Over to you, Romain. You're muted.
Yeah, okay, couldn't find the button, sorry. Yeah, my presentation is very related to the previous one. Though I will say, I should say from the beginning, like I'm no expert in internet in India. I'm a researcher at IIJ, and one thing I've been doing for the past few years is trying to measure network dependency, so I will explain what it means. And in this presentation, I'd just like to show how, so what are the tools we have, and how we can use that to understand the connectivity, some of the dependencies in India. And I think it was very nice we had this Anurag's presentation before, so it's gonna help a bit to understand. Okay, so what do I mean by network dependency? To explain what is network dependency, I'd like to take that example. And I was planning to explain about BGP and autonomous system and everything, but the two previous presentations already done a lot of this. What I'd like to say here is, okay, as you know, like the internet is a network of networks, or those ASs. And I think what is important here is that what it really means is that an AS will rely on other ASs to reach the rest of the internet. And we are also using BGP data. And from this BGP data, we try to understand the topology of the network. And we make this kind of graph here. And so here in the graph, a node is an AS. And the links here are the connection between the different ASs. And the blue one, so we are using both RIPE, RIS, and route views. And those blue nodes here shows our viewpoint, so it's from where we get the data. So what it means is that, for example, from this blue node here, 22.652, we can ask that AS, what is your path to, for example, IIT Hyderabad? And here we found that the path is going to Airtel, and then the NKN gateway, NKN core, and finally reach IIT Hyderabad. Again, I'm not an expert in internet in India, but as I understand, NKN is the academic network, And we've seen in the previous presentation, Airtel is a big ISP in India. So from this graph, what I think is very interesting is the structure of the graph. So you're going to see that almost all the viewpoints we're using, they have to go through Airtel and then NKN networks to reach IIT Hyderabad. And that means if one of these network, Airtel or NKN, has a problem, if has disruptions or large congestion due to attacks and things like that, then the connectivity of the IIT will also be impacted. So that's why we're saying, we're going to say that the IIT Hyderabad depends on NKN and Airtel. So that's really what we mean by network dependency. Okay, so the graph is nice for us humans to intuitively understand the topology, but for a lot of our research, we needed a bit more than that. We needed a metric so we can run analysis at a large scale for NEAS. So what we've done is we've designed a metric called AS hegemony. This was proposed a few years ago. And this metric quantified the dependencies of an AS compared to the other ASs. The way it works, so I'm not going to give the exact detail. It might, the technical detail might be a bit boring. But the way it works is we are taking all those AS paths from BGP data. Then we make a graph like the one I've shown in the slide before. And in that graph, we're going to measure the centrality of the node. And the centrality, so this is really the AS hegemony metric. The value range from 0 to 1, or you can see this as a percentage. I think most of my the score I will give after are in percentage. So you can see this as from 0% to 100%, meaning that 0% means like there is no dependency, and 100% means like a network depends entirely on another network. And the metric also account for the sampling bias. So if I go back to the graph here, this is like a view of the internet, but you should keep in mind that we are using recent route views, and this accounts for a few hundred ASCs. So we can get paths from a few hundred ASCs, but there is about 70, 80,000 ASCs on the internet. So what we have is really just a sample of what it looked like. And in this graph, you see like there is a lot of blue nodes. So those are all our viewpoints. In fact, they are not important for the, now we are looking at the internet connectivity of the IIT Hyderabad, but actually these nodes are not important for the connectivity of this network. For the one I took as an example, this 22652, it's a network in Canada. It's not at all related to the IIT. So our metric take into account this and try to make sure that we kind of avoid this bias we got from viewpoints. And finally, our metric also can, we can put weight on the different paths we have. So if you have like two different paths to the same destination, then we can weight them differently. For example, if one path represents a larger prefix than the other one, we might think this one is more important. And I will come back to this later in the presentation. Okay, so we have this metric. We are running these dependencies every day. And we made this website called the Internet Health Report. So here's the URL. You can go on this website, and on the search box here, you can just type AS number or the name of a network, and we're going to show you the dependency of this network. So for example, here I enter this NKN gateway network, and what the graph shows is, well, maybe it's not really clear here, but the line at the top at 100 is Airtel. So it tells us that this NKN again depends 100% on Airtel. And they also have a second graph here at the bottom, which tells us how many network depends on NKN. So that will be like all the ASCs that are downstream of NKN that depend on NKN. So there's about 70 of this network, and we have the list of the network, of course. And if you look at this list, you're gonna see like all the IITs and some of these research networks, etc. So this website shows these dependencies. You can, if you need this, the raw data, we have an API, so you can get the data, and we also have a Python library, so you can get also this data. Okay, so this is kind of fun. It's good for us like to understand the topology of the network, but you might wonder like what we are doing with this, why we are doing this. And the very first motivation was mainly for planning and some peering decisions. So if I go back to the example of IIT Hyderabad, so here it's clear that the IIT Hyderabad so depends on NKN and Bhatia. And we could guess that if there's a peering coordinator that want like more resiliency for this network, they could seek for another upstream provider. And so now they're using NKN, but if they have to choose an upstream provider, knowing those dependency, we can guess that Airtel won't be a good upstream provider for them because it's actually just increasing their dependency to Airtel. So they could choose another upstream provider. That's mainly why we designed that metric. And then we found that there's a lot of other application for that metric. One thing we've been doing is monitoring some of big routing changes that happen. So when there is like outages, DOS attacks, some misconfiguration, we can see that those dependencies sometimes are changing very quickly. For example, imagine there is, we have example of DOS attack. So we can see like this, like a type of DOS attack called carpet bombing, where you can see like a link to an upstream is DOSed, and you can see that those dependencies are gonna change. We have an example also where GitHub was under a DOS attack, and we can see that all their traffic shifting to Prolexic, the Akamai DOS mitigation service. So we can see those change in the topology. We had some research on using this dependency to classify BGP hijack and detect BGP leak. I could explain a bit more later if people are interested in this. We had a study on looking at the impact of geopolitical events, and we looked at when Crimea was annexed by Russia. So we could see the change, like the Crimean network, all the traffic was then shifted to Russia. This is something we could monitor. We had a study on internet flattening. And finally, we extended also this metric to measure the dependencies of an entire country. And this is really what I want to develop in the rest of this presentation. So the idea is very similar to what I've shown at on the very first slide. But instead of looking at all the paths to one AS, we're gonna take like all the AS in one country. So here in orange, and we're gonna look at all the paths to all the ASs in that country. So if we take this example, you're gonna see that this ISP-A has a lot of downstream ASs. ISP-B has only one. And so if I run the exactly same metric, then I will see that this country has a strong dependency to ISP-A and a smaller dependency to ISP-B. So this is just like doing exactly the same thing, but using a country instead of an AS. But what we find interesting for countries is the topology is important, but also one thing that people are more interested in is how the population of the country is distributed in the topology. So we can, using the APNIC population estimate, the eyeball user estimate, we can guess how many eyeball user there is in each AS. And this time we're gonna run again our metric, but we're gonna weight each path based on the number of eyeball user they have. And in this case, when we compute network dependency, we're gonna find that the population of this network, of this country, depends strongly on ISP-B and much less on ISP-A. So we have, for countries, we have those two different views. Like if you want to look only at the topology and I mean the ASs in the country, or if you want to look at the population. Okay, so if you if we go back to our website, you can also give the country name, and we're gonna give you all these dependency we found for a country. You can type any country, and the result will be for these two different views. So we're gonna give the view weighted by eyeball users, and the other one weighted by autonomous systems. And I'd like to go, so these are the results for India, and I'd like to zoom on this and explain a bit how to read that table. And so then you can do the same thing for other countries if you're interested in this. So if we look at the first line, this is geo, and APNIC tells us that about half of the population in India is using that network. And so this percentage here, 151%, is the dependency score. So there is about 51% of the population that depend on this. And then we break down this 51% in two numbers. The first one is direct. That means the population is directly served by this AS. If we look at the second line, we have the same total number, 51%, but this time we see that it accounts for the indirect. And indirect means that the population is not hosted in this AS, but that population, this 51% of the population, has to transit through that AS to reach the rest of the internet. Okay, so this goes back to the previous presentation, where we can see that there is one AS that is really for the broadband users, and then there is one AS that does the transit. So this is the case for Geo. For Airtel, it's very similar. The numbers are a bit smaller, so it's about a third of the population is depending on Airtel, and again they have one AS that hosts all the eyeball users and one that is doing the transit. One thing that is interesting for Airtel is it has another high value, but this time for the AS dependency, for the topology. So what we found is there's about 50% of the ASs in India also depend on Airtel. So Airtel has these two roles where it's gonna serve the population and also a big part of the infrastructure in India. And if you look at, I'm not going to go through the whole table, but if you look at the other big numbers in terms of topology, you will see here at the bottom there is Tata. We have two networks for Tata. And again, this 6453 is the tier one, like it was repeated many times before. So this tier one provide connectivity to this 4755, which seems to be a domestic network in India. And about a third of the ASs in India are using Tata as a transit. So I could go further and like I've skipped here, I skipped Vodafone, but I could go further and complete that picture that just give us like a very broad overview of what the internet in India looks like. I think with the previous presentation, now we have a very clear picture of what the internet in India looks like. It's an exercise I like to do in this kind of presentation, so I can hear from the audience if this makes sense or not. I'm just reading like the result we got from our tools. But what I'd like to point out is this can be useful if you're interested in other country. Usually people knows more or less the situation in their own country. But for ISP that want to have a presence in a new country, they have to understand the market in that country, and this could be a way to understand that. Okay, so that's all I had for my presentation. So the main takeaways are that we are developing tools to measure ASCs and countries' network dependencies. All these results are based on BGP data. I didn't say much about this, but that also include some limitations. And the data, all the data is available on our website. We also provide all the tools if you're interested in this. And well, if you want to contact me, here's my email address and my Twitter account. Thank you very much. If there is any question, I'll be happy to answer.
Thank you, Romain. That was an interesting talk again, and it is interesting to see how tools that one group of people are building can actually be used by others to confirm what they have observed. And for example, what Professor Chakravarty presented or what Anurag presented. I think Anurag has a question, so go ahead, Anurag.
Sure. Romain, thanks for the talk. It was really good slides. One thing which seems to be missing from this data is the fact that you can't really find peering relationship these days, especially with between small ISPs and the content players, because small ISPs would typically not feed those relationship to a route collector, and the content side would typically not feed either. So both sides would not feed it to any public collector, and hence you will not realize that so much of peering already exists. So in case of NKN, I'm personally not aware, but I won't be surprised to find that NKN is paired with, possibly 8 to 10 large content players, and possibly 70 to 80% of their traffic is flowing over peering. So sure, they may have single point failure in AS9498, but that's for 30% of their traffic. They could still reach root servers. They could still have the DNS functioning properly. They could still have the top content working properly on that one. What do you think about that? Is there a way to measure that as well?
No, that's a very good point. Yeah, that's a very good point. And that's what I meant by at the end, like I say, like, oh, we are using only BGP data, and that means a lot of limitation. Like you said, like all the peerings that we cannot see. And also you made a very good point is I tried, I don't know if I did good or not, but I try usually when I have this presentation to say like, okay, this is the topology. It's not the traffic. Traffic might be very different. So we are counting number of paths, and it's just like all the AS paths from all the route collectors. And it's possible that there is no traffic actually going from, for example, the IIT to any of these AS. So yeah, it's more like the topology. We are interested in looking at this in terms of traffic, but this is something that is harder to do at a large scale like that. So for example, we could, an ISP could just take its own traffic, look at his routing, look at all his paths, and then try to do the same computation, but instead of weighting by population or by prefixes, then it could weight by the traffic it sees going out and in from its network. And that's, I think that's yeah, that's, I mean, your point is very valid, and to make it more useful, we need traffic from people, but it's something like they don't share usually.
Sure, thanks.
So we have one comment in the chat. So Romain, if you can kindly explain what is country network dependency one more time. Yeah.
So the country network dependency is a country, and now from Anurag's presentation, I understand that for India this applies very well. Is a country has connection to the internet, as like different way to connect to the internet. Of course, there will be a lot of inner traffic or a lot of inner interpath in the country, and there is like international paths that just go outside of the country. And here, what we try to understand is what are the different gateways, but in terms of AS, what are the different AS that allow us to reach a network? And we try to quantify this. So what are the network that, if I'm outside of India, what are the network that I have to go through to reach people in India? And if this number of network is very small, then there's this kind of topological bottleneck. And this is like it could be a single point failure. So if this network goes down, then the country could lose like international connectivity. So this is what we are trying to measure, and this is what we mean by network dependency. So in this very simple example, you could see that if those tier 1 goes away, then maybe that network won't be able to reach the internet anymore.
Okay, thank you, Romain, for this explanation. Do we have more questions? I don't see any more questions. Maybe quickly, I will jump back on what Anurag was saying. Maybe a nice addition to your study, Romain, would be to run traces in between the networks and actually see, the reachability kind of, and really understand. So because you have what you're showing is control plane data, and having data plane information might be a good addition to that study.
Yeah,
great.
Sure. That's something we're working on. Yeah.
Perfect. Thank you, Romain. So let's move to the last but not least speaker today, who is Hannah. Hannah is a colleague of mine. He works for the Internet Society. And you can introduce yourself, Hannah. Thank you. You're muted at the moment.
Thank you. Yeah, thank you very much, Amreesh, and hello, everyone. I'm honored to be with you today in this event, and I'm glad that I've joined you from the beginning, where I learned a lot from the presentations. I try to keep my speech very brief in respect for time, and what I'll be talking about today is how measuring artificial internet limitations, including shutdowns and other disruptions around the world. So what do we mean by artificial internet limitations? Well, it is an umbrella term that includes any activity that limits access to the internet. And by artificial, we mean it's the opposite of natural, in that it is designed that way. It took someone some time to change the configuration to limit access. And by limiting access, we mean it can include service blocking, bandwidth throttling, you name it, all the way to full internet blackouts or full internet shutdowns. At Internet Society, we started to look about how we can have one source of information where we can include information on shutdown events in general. We partnered with key data providers to include one area of focus within our Pulse platform that is dedicated to internet shutdowns. So how do we measure these artificial internet limitations? The previous presentations showed in great detail how we can look at the internet infrastructure level and see changes happening there in terms of peering, routing, and so on. However, sometimes it's also necessary to just listen to the people and to the local reports, and I'll come back later on why this is important. Generally, we can have two points of vantage for the information, either from within the network or from outside of the network. As you can see within the network of networks, we can feel changes in traffic, and we sometimes try to find evidence for why these changes happened, and we end up with a shutdown claim. We try to collect as much evidence as possible and as much information as possible to define the scope and scale of that specific limitation or shutdown. In addition to collecting data, we do not produce our own data so far. What we do is we curate data from different sources and try to make sense of them to understand what is going on the internet in terms of shutdowns and limitations. We work with data providers, and we also work with communities on the usage. The types of data sources that can be used for identifying artificial intelligence and that we rely on include dedicated observatories like Kaida's IODA, which was mentioned earlier today, that looks at basically changes from the outset on traffic and routing, as well as tests from directly to the networks. We use data from the Open Observatory for Network Interference, ONI, which relies on data from probes from within the networks that are run by volunteers. We also have reports from internet services, which is very, very important because this gives us, I would say, different overview of what is going on within an area where the internet is being limited. We can see drops in access to YouTube, for example, or to Google web search, and we can compare to patterns of regular usage to clearly identify changes in traffic. Google makes that available through its transparency report. Cloudflare makes similar data available through their radar. And from there, we curate the information to our platform, Pulse. There are many other sources. These are the main types of data sources. What are we seeing? We are not seeing that full blackouts or full shutdowns are less common, but when they happen, they are more blatant. A country says, yes, I did cut the internet. Artificial internet limitations are becoming more targeted, local and even hyperlocal, and harder to detect. In the first presentation, Sambuddha mentioned the issue of wire trapping through middle boxes, and that is not easy to detect around the world. Some shutdowns targeted specific access methods, shutting down mobile data or limiting access to specific websites on mobile data compared to fixed lines. The target limitations are also increasing. We have seen in some cases limitations that would look like throttling Facebook live streaming around a very specific space, like Blick Square, within a very specific time during a protest. In India, we are also seeing local and hyperlocal limitations. Specifically, however, in India, it's more related to internet shutdowns. They're becoming smarter, as with the issues related to middle boxes that were mentioned earlier. And they're harder to measure from the outside, because when a shutdown affects 1% of the total population, or 5% total, or even 10% of total population, that doesn't really trigger a good drop in the overall traffic. So it's very hard to measure shutdowns within India from the outside, which means that we need to rely on information from inside the networks, which include testing through UNI probes and other measurements from within the network. In general, at the Internet Society, we believe that shutdowns harm societies. They harm economies and the global internet infrastructure. And thus we try as much as possible to lobby against any shutdown or any artificial internet limitation. This is also because they are generally inefficient. As you may know, and you may have experienced, people always find a way. People always find a way to access the information they needed. You will always find a way to communicate with whomever they want to. People basically always find a way. And that's basically what I wanted to share with you today in very, very quick and brief points in respect of your time. If you have any questions related to what the Internet Society stands for when it comes to shutdowns, our official statement is in the link here. I'll put it in the chat in a minute. And if you wanted to learn more about our measurement activities on the internet, including the shutdowns, internet resiliency, and enabling technologies, and a couple of other focus areas that are coming soon, please visit our website, pulse.internetsociety.org. Thank you very much. And if anyone have any questions, please don't feel shy to contact me at any time.
Thank you, Hannah. Thank you for giving us an overview of the shutdown focus area on which the Internet Society is working on, and the different data sources and aspects of shutdowns that we are collecting. Thank you also for keeping it short for the interest of time, as we have reached almost the end of the session here. So do you have any question for Hannah, or actually any one of us? Please feel free to ask your question, either in the chat or, yeah, we have one from Sambuddha. Proceed.
Hi, Hannah. I have one small question for you. You said you require inside information to detect this shutdown or censorship. It's very true. But have you looked into the IODA project from Qaeda? they are looking at shutdowns. They don't call it categorical shutdowns, they call it shutdowns and disruptions, stuff like that. And they basically look at global routing tables, trace routes, round trip measurements, etc. to give basically they give a confidence score to say whether some particular event is occurring or not. You kind of looked into something like that, or are you looking into that?
Yes, actually, we use IODIS information or IODIS data a lot in our work. And however, what I meant that in the specific case of India, where or any such large country, drops in traffic, whether they were on ASN level or on regional level, does not always reflect or give us confidence in a shutdown.
I agree. Yes. Yeah. That's all I wanted to ask. Yeah.
Thank you, Sambuddha. Anyone else? I don't see any more questions. So in that case, I think we can wrap up here. I would like to personally thank all our speakers today for your time and also your effort working on the slides and presenting today. I would like to invite Bala now to give the closing remarks.
Thank you. Thank you, Amreesh, Phokeer, for wonderfully moderating the entire Internet Measurements, Global Policy and Online Privacy workshop, which was conducted in collaboration by ISOC India Hyderabad chapter and with the support of Internet Society. It is definitely a great privilege for me to thank all the wonderful experts who have shared their work, experience, and expertise during this workshop. First of all, I'm thanking Sambuddha Chakravarty for bringing us the full perspective of censorship infrastructure in India and how censor traffic is managed and implemented by the internet service providers. It was a wonderfully received, and it really engaged personally me in understanding how important is the censorship traffic. Thank you, Sambuddha, for giving a very insightful and detailed talk. Next, I would like to thank Anurag Bhatia for delivering a very interesting talk on Indian traffic getting routed from outside India. Your expertise in sharing the optimizing routing across thousands of border gateway protocol adjacencies and putting tools to monitor it is a real insightful, and it really attracted many of the participants and delegates to understand the deeper work, a practical way of looking at the things and understanding and interpreting the same. Thank you, Anurag, for giving your practical view of that. Definitely, as we are trying to do this workshop, I believe we all know that internet is composed of networks that rely on each other to provide global connectivity. And I was reviewing the blog written by Romain, and it really a very, very fascinated way he has provided the view where he was trying to touch upon how the reachability of the network depends greatly on the connectivity of other networks and the understanding of the interdependencies between the autonomous systems, which is truly essential for deployment decisions, routing decisions, and also the connectivity troubleshooting. And the way it has been defined helped us to currently look at the new metric called AS hegemony. And Romain has delivered a very, very insightful talk. Thank you, Romain, for bringing that perspective of AS hegemony to measure the network dependency. Finally, I would like to thank also Hannah Kritam for sharing the outside-in view of internet shutdowns, outages, and other disruptions. A very short but very, very precise talk, giving us the full perspective and very, very insightful. Thank you, Hannah. And finally, I would like to extend my thanks to Mohan Raidu, President ISOC India Hyderabad chapter, and also the other executive members of the ISOC India Hyderabad chapter for supporting to drive the Internet Society initiatives within this particular part of the geography with a greater commitment and passion. Finally, I would like to say that every such kind of a workshop which is trying to drive interest in the internet is done for a purpose. And if the purpose is met with a passion, if the purpose is met with a need, I believe it will drive a lot of impact and create a huge reach and attract many more to work in the research areas associated to the internet and support Internet Society initiatives. Thank you. Thank you, Amreesh.
Thank
you
you,
wonderfully
Bala.
moderated it.
Thank you very much.
Thank you, Amreesh. Thank you, Bala.
Thank you. Thank you, everyone.
Thank you, panelists. It's been a wonderful workshop today. I think we should carry forward the exercises in the internet measurement through a series of activities. You're most welcome to be in touch with us and advise us to do some projects and activities in internet measurement. Thank you. Thank you, the participants, for sparing your valuable time. Thank you all.
Thank you.
Thank you.
So you will all receive an email with the workshop report and also the link to the slides, hopefully very soon. Thank you again.
Thank you.
Have a nice day. Bye.
Bye.
Thank you.
Thank you. Bye-bye.
Thank you.